Yes, so that's the beginning of the first session, and I would like to welcome our keynote speaker, Alejandro Russo. Alejandro and I went a long way back. We were colleagues back at Chalmers University of Technology, but I'm still going to look at the bio he has provided because there's so many great achievements that I fear that I may forget some. Have a rest. Yes, so Alejandro is a professor at Chalmers University at Technology, and I would like to add that his career basically rocketed. He finished his PhD ahead of the time, then very quickly move on to assistant professor, then very quickly to be promoted to associate professor and professor. That was many years ago. Then he has worked on the intersection of functional programming, security, privacy, and systems. Right? So for us who has worked in the intersection of areas, it is actually a very tricky place to navigate. Right? You may enjoy great success, you may fall in the track. Nobody likes you, nobody publish a paper. But Alejandro somehow managed to be a great success. He is a recognized figure in programming languages and also in security. His research ranged from fundamental aspects of security to practical ones. And he has a close connection with Stanford, which is also kind of prestigious. Just to mention, he received the most influential paper award at ISFP 2022 for his library, I believe, for security, language-based security in Haskell. And as well, distinguished paper award at POPO 2019. Just add to that list of already remarkable achievements as an academic, he recently has become a CEO of a startup called DPella. It is a startup providing differential privacy solutions in Haskell. Right. So I believe that's going to be his topic today, that we'll be talking about from theory to practice, crafting differential privacy systems with Haskell. And I was told that there will also be a connection to a partial evaluation, very fitting for this workshop. Thank you.
Thanks, Wayne. Thanks a lot. Thanks a lot for the introduction. Yeah, I can tell you one connection. I'm super honored to be here. So let me tell you one connection I read with PEPM'. My first ever paper that I submitted to ever computer science conference was to PEPM'. Like 19 years ago. Yeah. Let me see. All right. Yes. Today, essentially, I'm going to take you in a journey that I've been taking in the last 3 years, where I've been working on data privacy topics from a PL perspective, and as well a little bit on the system perspective. We will do some live coding. You will learn something about differential privacy, and then I will give you some reflection about, trying to take something like this into practice, in case you are motivated to do the same with your research. All right. So let me start with some introduction. So today it's all about data. Like never before, companies and governments are collecting data, and they want to mine that data to learn how customers or citizens are using services, okay? And you want to learn about trends in population, what you call as data insights. And you want that data to be shared among your own partners or among different governmental entities. And the main challenge is how we do that in a way that by sharing the data, and someone observing that data, we do not reveal who is in the data set. Okay? So, because it could be like, it could be like, people sick with certain disease. You share analytics, you don't want people to guess by looking at analytics who is sick. So this is the main problem that we have today, data sharing and privacy. How do we share insights about data sets while preserving privacy? This is a hard hard problem. And industry is screaming for this. But not take my word for that. This is the Swedish IMI, the Swedish Agency for Regulating GDPR. GDPR is a regulation in Europe that tells you how to handle personal data. And they got a mandate from the government to say, please investigate what is the most roadblock that we have to make Sweden the data-driven nation, the leader data-driven nation in Europe. And it's like this, so I don't expect you to understand that, but it says more or less that data sharing is without reason the most difficult part. Data sharing while preserving the confidentiality of the information, like only the parties authorized to see it will see it, but as well to preserving the privacy of the individuals. Okay? But there are many, many ways to share data and privacy. There are different scenarios. So let me set up the one that we're going to use for this talk. In this talk, we're going to consider someone called data curator. Data curator is someone that owns a data set and cares a lot about privacy. Imagine you are the CIO, the Chief Information Officer in a company, and you have your customer database. You care about the privacy of that. Okay? Then on the other hand, you will have the data analyst who wants to extract information from the data sets, okay, in the form of analytics. So we need a technology, we need a technique that enables the data curator to share those insights while preserving the privacy of the individuals. So data curator cares about privacy, not so much about the analytics, and analysts care about getting insights, not so much about privacy. We are going to put in these black and white terms, okay? All right, this talk is going to be based in some papers that I've been working in the last 3 years, plus some unpublished work, okay? So what I'm going to present you here is a system called DPella. I'm describing, I can explain what it means. Usually I cannot explain, so I will do it. It means differential privacy in Haskell with accuracy. And you will understand that what it means in the end of the talk. And the idea is like a data analyst in a DSL writes some Haskell code to do a query on the data set, and then it gets analytics back. And all of that while having certain privacy guarantees. Okay? All right. So to preserve privacy always comes to a cost. Protecting privacy is never for free. Okay? And the techniques that protect privacy when you are releasing information, like we are allowing people learn from our data set, the price to pay is the accuracy of the analytics. How accurate is the data? The more privacy protection you have, the less accurate it will be. The less accurate it is, the less privacy you have. Okay? So in this talk, I'm going to present you differential privacy, which is a privacy definition that has some mathematical foundations that allow you to reason about this trade-off between privacy and accuracy. Okay? How much privacy we have and how accurate or useful are the analytics I will get. Okay? So now I will go through a background in differential privacy, very quick background. So bear with me. So as I said before, differential privacy is a definition. It's from 2006 from some theoretical computer scientists. And the definition entails to consider data sets, right? And data set here, we're going to consider that a row in the data set has information about one individual, and that's it. So every row has information about individuals. Then the definition considers adjacent data sets. Those are data sets. If you see D1, the difference between D1 and D2 is like you remove one row. Okay? You remove one row or you add one row. You remove one individual or you insert one individual. The definition also considers a randomized query, Q tilde. It's randomized, means like every time that you run the query on the data set, it's likely to return different results. Okay? And the definition relates the probabilities to run the query in D1 with D2. Right? It says, if you run the query in D1 and you observe something, that's what it says belongs to S, that's something, is similar to running the same query in D2 and observe the same thing, module some factor e to the power of epsilon. Okay? So it's telling you that running the query in one data set when another one where you have removed one individual is almost the same in this notion. which means that it's hard to see where the result comes from, if it comes from D1 or from D2. So in that way, you protect the presence or the absence of an individual. Okay? And this is true for all individuals that you choose to remove from the data set. Let me show you more graphically here. So you have, Q tilde applied to D1, now it's a distribution. Q tilde applied to D2 is another distribution. And you can see here that the probability to observe 0 in D1 or in D2 is not the same, but there is a gap there. And that gap is regulated by epsilon, which is called the privacy parameter. The smaller the epsilon, the distribution will get closer and closer. The harder it is to distinguish if the result comes from D1 or D2. The bigger the epsilon, the more far apart the distribution is going to be, the easiest is to distinguish if it comes from D1 or D2. It doesn't mean that it's going to be easier, but it's easier. Okay? Right, and this definition gives origin to some composition principles that are very useful for writing or building systems. One is called sequential composition principle, which is the most simple one, that says if you have a randomized query that is epsilon 1 differentially private, satisfies the definition, and you have another one that is epsilon 2 differentially private, and you want to run them both as a unit, as a one, it's like you put a semicolon in between. Sorry for using a semicolon in a functional setting, but yeah. So the whole block is epsilon 1 plus epsilon 2 differentially private. Okay? So if you have differentially private queries, you run them in a sequential way, I still have a differentially private query with epsilon 1 plus epsilon 2 as a privacy parameter. Okay? And then you have the other one, which is called the parallel composition principle, which says if you have two queries, again, differentially private ones, but you run them on different part of the data set that is joined, if you run them both and obtain the result, the whole block is going to be differentially private, but where the epsilon is the maximum between E1 and E2. Okay? So don't worry so much about the parallel composition. This is the one that we're going to use in the talk. But just for you to get an intuition, like this definition has some composition properties that enable you to build systems. Right, and we're going to use the sequential composition principle to define what is called a privacy budget. The data curator, remember, is the one arguing for privacy, and he set up a privacy budget and epsilon, right? Let's say 2. You can see that epsilon like a bag of coins, right? And you want that all the queries that you're going to do to the data set will never be more than 2 epsilon differentially private. Okay? So then you distribute the coins against to the different analysts. So the first analyst, let's assume, receive 1, and he does a query. When you do a query, you need to pay. You need to consume the coins, right? Once you consume it, they get burned, right? And for example, 1, you burn it, you get some analytics results, and then the rest that also receive tokens, they can pay for that and get analytics back. Since you have epsilon 2 as a privacy budget, whatever you do, the composition of all those analytics will be differentially private, but never more than 2 epsilon differentially private, right? Once you exhausted the budget, right? When it disappears. You cannot query the data set anymore. Okay? Right, so how do we build these randomized queries? And I'm going to show you one simple way to do it. So then, you have the whole picture, how this works. Imagine you have the query that say, we need to count how many employees have salary bigger than 60K, right? The way that we're going to create this randomized query is taking the original query, the privacy parameter, and we're going to synthesize the Q tilde. And we're going to do it in the following way. We just add noise to the original result of the query. But that noise needs to come from a special distribution, which is the Laplace distribution centered in 0, with an scale of sensitivity over epsilon. I will tell you what that means. But the scale regulates how pointy the Laplace distribution. The Laplace distribution is like this. It regulates how pointy it will be, okay, or how flat it will be. You see the privacy parameter there, epsilon there, and the sensitivity. I'm going to be very informal, but the sensitivity is like if I change the data set, how much the output will change. if I remove one person, I run the query, and now I remove one person, and I run the same query, how much that query has changed? Because here we are counting, if I remove one person, the output will change almost once. If I remove 2 people, the count will change almost 2, right? So the difference between what I change in the input and when I change what the output changes is a factor of 1. So we say that sensitivity is 1 for counting. All right, the good thing that all of this, you see a lot of heavy, I don't know, heavy math, but some math. And we are going to package all of that and give you a DSL where you can write queries which are differentially private and support this notion of privacy budget. Okay? And you are the data analyst, and I'm going to give you my DSL, right, to play with it. So the first thing you need to do is to learn about 3 abstract data types: datasets, value, and query. Dataset means it's a dataset. It has 2 type parameters. We skip the first so far. We focus on the second one. It's the type of the row in the dataset. Then we have values, which are values that has been generated with the Laplace mechanism. So values that where noise has been injected. And then we have queries, which has a monad structure. It means it's a collection of instructions. In DPella, we have 2 kinds of instructions. One is called transformations. It takes a dataset and returns a dataset. You can filter it. You can map it a function over a row. You can union, intersect, group by, and so on. So DPella supports to do those transformations and any combination of it. And then the second kind of instruction we will have in queries are measurements. This is when we learn from the data. And that's when we need to inject the noise, right? Because those are the insights that we're going to share or publish. The measurement is counting, like the query that you saw before. We are counting certain events, the size of a data set. We sum a column, or we do an average. Okay? And DPella supports you take all these results and do any linear combination of them. Okay? All right. Are you ready to play with it? All right. Let's take one transformation and one measurement, and then do something with that. Okay? All right. So this is one transformation called DPware. It's a filter. You give me a Boolean function, you give me a data set, and I give you the query that filters a data set. Let's take the measurement of counting. You give me an epsilon, how much you are going to pay for the query, the data set, and I return you a noisy value, the result produced by the Laplace mechanism. Okay? All right. So this is risky, so we see how this goes. But let's do it. All right. Here, what I'm going to take is a data set called adult, which is a famous. Oh yeah, sorry. Yeah. Let me see if I can. Yeah, sorry about that. I'm going to mirror the displays and then I keep it like that. Let's see. Yeah, now you see it? What? Sorry, give me a second. Yeah. Sorry, I didn't realize about this. Okay, keep changes. Now you should see it. Now you're with me? Yeah. So I have an adult data set that is about information about the population, right? So it has an age, the work class, education, the occupation, the relationship. And you see that there are like 33,000 rows, okay? So let's model that into Haskell. So here I have a file that is going to use DPella. And for every column in the dataset, I assign a type. Columns in dataset are known as attributes. So for every attribute, I have a type. And then the type of the row is just a record. Okay, that you see here. Age, work class, blah. Okay. So now let's build a simple query that I want to know how many females are in the dataset. Okay. I create a function that you need to provide the sex that you're going to filter upon. In this case, it's going to be female, but let's keep it general. Epsilon, how much you're going to pay for the query. The data set, which is the data set adult. That's why the type of the data set has the type from adult. You want to make it bigger? Yes. Yeah, sorry. Yeah, let's move this out. Is that okay? All right, that's better? Yeah, thanks. All right, so here what we're going to do is like, we're going to use DPWare. So we say, okay, I need to filter the data set. Some function, and then the data set I'm filtering is DS. So I say, well, give me the row, give me the input that you want to be interested in, the sex you are interested in, right, S. And then I say, well, I extract from the record the sex of that person. All right? And now what I do is a dp count, I pay epsilon in ds prime. Okay? The query is ready. Now what we can do with DPella, we can check, is this query using epsilon? How much budget is using? How much coin is burning? Right? So I can say, well, let's, I'm going to call this function, call budget. Give me a query, and I give you how much budget is there. Okay? So, and I say, well, let's do the budget of simple count, female, epsilon, let's say 1, and I need the data set. But I don't have the data. The good thing is all the analytics done by DPella are data independent. So you don't need the actual content of the data set, you need a symbolic data set. So here I put symbolic data set, and I will explain you what this add1 means in a second. Okay? So if you see, I apply all the parameters of simple count, and I have a query, I evaluate, and it says 1. Right? But now we can do like this. We can say, well, maybe the programmer did a mistake and took the epsilon, and I thought, okay, I can use it 10 times. Right? And I call again. Now it says 10. Okay? And you can see here that these are all Haskell expressions. Okay? Right. Now we can run the query actually. Let's go back to 1. How it was before. Now we can run the query, and the query will load all the data from the adult data sets. And this is we are going to use DPeval. And let me show you the type of DPeval. Give me a function that takes a data set, ignore the 1, and returns a query. Give me the content of the data set, and the epsilon. This epsilon is a privacy budget. And then I will run it. So DPeval is used to set up the privacy budget of the query. So here, we can see here, like, I want to run this with we say epsilon 1, and the budget is 1. So that should work. And then we say, okay, there are around 10,000 females in the data set. That number has noise injected. How accurate is that number? We will see in a second. Right? But we can see here it's just like if we try to use more budget, that's what is allowed. It will say not enough budget. One invariant that you should think when choosing how much to pay for a query, the more you pay, the more accurate it will be. The less you pay, the less accurate it will be. Okay? So here, if I pay just very little, we see that the value is 3,000. If I run it again, you see there is a lot of noise being injected. Okay? We will see how to reason about the accuracy in a second. Okay, great. All right. So now, for the sake of completeness, let me tell you about the parameter S here. Yeah, we have seen so far that when we do this reasoning about how to calibrate the noise, we say we need to understand the sensitivity of the measurement we are doing. If it's accounting is 1, because if I add 1 person or remove it, the result changes at most by 1, because I'm counting. We say sensitivity is 1, great, we inject the noise, everything perfect. But there are situations where if you do some transformation before, this relation between how much you change and how much impact your output doesn't hold. Let me give you an example. For some reason, you take the table of this adult table and you separate between European and Latin Americans, and then you just join them. Right? Very inefficient, but some way to do transformations. If I add or remove one person here, and the person has double citizenship, it will go in both tables. When I do the union, I will have that record repeated. So now, I add or remove one person, but the count will be changed by 2. Okay? So that's what this S parameter is about. It's called the stability of the table, which says when you do a transformation, how much removing or adding one person gets magnified in the resulting table. So here, we are filtering, the stability is 1, because if I add or remove one, when I filter, I will see that once, at most once, right? Or it's not there. So, but in the union, it's just addition of the 2 stabilities, right? We keep track of that, and we adjust the noise so that now it is differentially private. Now it's taken into account that transformation can magnify the presence or absence of a person plus the sensitivity of the function. So in this way to do things is differentially private. Okay? All right. So and here you can see the rest of the transformations, and we play with where and union, and you can see union there, and how it's using the type level numbers to keep track of the stability. Right? And you have DP count here, sum, averages, and maximum. Right? The rest of the API, and that's it. There is no more. Okay. All right. So let me talk about the accuracy. How accurate are our results, and how can we reason about that? This is something that usually lacks in differentially private tools, but in DPella we decided to embrace it from the beginning. Right? Accuracy is as important as privacy. Right. So we need to define accuracy. How do we do that? Well, we need to reason about the actual result of the query. Remember, we have a query Q and a randomized version of that called Q tilde, where we check noise from the Laplace distribution. If you run the query in D, it gives you 1 point. That's a real result. If you run the query Q tilde, it's a distribution. So we need to reason about how far the points in the distribution are from this real point. And the way that we're going to do that is by using confidence intervals, and I give you the definition. It's like this. You're going to reason about the distance between a point in the distribution Q tilde and the real point. The important thing here to notice are 2 parameters, alpha and beta. Alpha is the error, and beta is the confidence parameter. Okay? And you need to think it a little bit in the dual way. You say, like, if beta is 0.05, it means that 90% of the time, the distance between a point in the distribution and the real point is bounded by alpha. So alpha is error with 95% of confidence. Okay? All right. So we continue with this. And hopefully, yeah, excellent. That's everything fixed. Great. All right. So, yeah, let's go back to this the query, the simple count, this one that we have done here. Now what I can do is, like, I call this function accuracy. It says, give me a query that returns a noisy value, give me a confidence interval, a confidence parameter, and I give you the error. Okay? So we can run it. Accuracy, and then I will take this. That was the query. Again, we don't need the real data set. Now, sorry, now you see here the number 1. The number 1 is the stability of the table. And the first table that you have in the system, the one that derives all the transformations and so on, has a stability 1. So the first table ever has a stability 1. Because by definition, remember the HSN definition was a difference of almost 1 in the records. Okay, right. All right, so we go here. Let's say 0.5. 3. With 90% confidence. That's error. It means that, remember that we run this when epsilon was 1. Sorry, we run it here with, let's run it again, when epsilon was 1. Remember it was 10,000, right? 770 plus minus 3. Okay? And now we can start seeing like, okay, but instead of paying 1, that's too much to pay. I want to pay much less. Remember I told you, less you pay, more privacy, but less accuracy. Now that's error, 300,000. Okay? But you can reason now about privacy and accuracy balances, the trade-off that between them. Again, this is all Haskell expressions, right? All right. Let me show you the key feature, one of the key features that appears in DPella that is not anywhere else. And this is about how we compute the accuracy of aggregation, when you add noisy quantities. Okay? And I'm going to show you that with an example. Here we have like, we are counting over 2 different data sets, whatever that is, and then you add them up. What do you learn from physics? You know, in physics, well, not physics, but very basic physics. Like, you know, you measure one quantity, it has certain error. You measure another quantity, it has certain error. Now you add those quantities, what is the error? The most brutal thing you can do is the addition of the errors. Okay? So that is known as a union bound in more formal terms. And I'm a little bit informal, but this is intuition. You know? This is union bound, means like I'll just add errors. Okay? So in DPella, we use a theory from probability that is called concentration bounds that says, and one is called Chernoff bound that says, if you know that distributions are statistically independent and come from the same distribution, except the parameters of the distribution, if you add them up, the error can be computed in a way more accurate way. But the challenge is how we detect the statistical independence. It means like when I sample here, I don't use this value to do the next sample. Right? So I've been working a lot on information flow control. That is all about detecting dependencies and independency of things. So we're going to use taint analysis to detect the statistical independence. Okay? Let me show you how it works DPella internally. So we have the first query. We'll give you, it doesn't matter the triple here, focus on T1. This is a count, it's a fresh sample. So I put a tag, T1. Right? This is stored inside this value. Then I run the second count. It's a fresh, the first and the second count are not related. It's a fresh sample. So I put the tag T2. Okay? Then I do the addition. Is addition statistically independent? No, it depends on 2 sources of noise, because I'm adding 2 quantities that come from different sources of noise. So it's not statistically independent, it's tainted. Okay? So now DPella will ask, to compute the accuracy of the addition, DPella will ask, is there one of the operand? If one of the operand is tainted, or there is one tag that gets repeated, if that's not the case, I can apply union bound or the best between union bound or Chernoff bound. Why is the best of both? Because Chernoff bound wins asymptotically, but there are some cases where union bound wins, right? And we are developing a programming language, so we need to consider all the cases, right? So we need to do that. So, yeah. Now let's change the program a little bit to see what happens when this is not, when the answer is yes instead of no. Let's add this scalar. You know, multiply B1 by 2, that's B3, and we just add them up. Now we have a value, which is B3. We have the same tag as T1, because it was derived from the source noise of T1. Now when I add the 3 values, there is one tag that gets repeated. All right? So then I cannot use chain of bound. The best between chain of bound and union bound, I can only use union bound. Okay? And let me see how I'm doing on time to see if we can do. I think I will skip the demo, but for this part, let's do it. I'll do it quickly. Right. So what we're going to do here, just you see the difference between the union and the chain of bound. I'm going to do n fresh samples of, I'm going to call DP count on the same data set, but you can imagine these come from different data sets, just for simplicity. I would say, well, I need to create a list of values somewhere, and I'm going to return the addition of this list of values. Okay? What we're going to do here, we're going to say, well, DP count, EPS, DS. This is the computation that we want to do. We're going to repeat it n times. And each time is statistically independent, doesn't affect the other sampling. So it's a replicate n. And then I need to do sequence, I guess. So sequence, should make sense, yeah. Right? So we have the query. N counts, and then I add them up. What is the accuracy of that? Right? We say, well, accuracy of total count. Let's do 100. I don't need a data set. Epsilon, let's say 0.5. And let's take the error with 99% confidence. So then we know, it's kind of the worst case. 130. Okay? All right. Now let's do the opposite. Let's do adding the same value 100 times. There is nothing more dependent than adding the same value 100 times, right? So what we're going to do is the do. We say, give me a value, DP count, epsilon ds, return at replicate n b, I guess, yeah. All right, so let's do the same thing as before, compute the accuracy. And now this will only apply union bound, okay? This one in the sample here was applying the chain of bound, right? Total count 2. Yeah, correct, thanks. Almost 2,000. Okay? The good thing is, like, you as a developer, you don't need to worry about it. And if in addition, you have some that are independent, some that are not, DPella will figure out how to split them and apply the best it can. All right, so these are very simple examples. Can you do more complicated analytics? Yes, histograms. That's the code. CDS, cumulative distributed functions. You can do it like this. You can do it like that. Sorry, like this, like that, or like that. Which one is best? I don't know. You go and figure it out. Okay? You can use budget and accuracy and analyze which one is the best according to your parameters, etc. Okay? So, quickly, I present you the very simplified version of DPella, so using the Laplace mechanism. But actually, DPella supports different notion of, different definition of differential privacy. And not all of them are compatible. Not all of them you can cast from one notion to the other one. So the queries are all indexed by the privacy notion, the definition of differential privacy that you are using. Okay? So, to recap, we have a query that we can analyze using the function budget, and that will take the query and will run a symbolic interpreter to obtain what is the budget that the query is using, and it's going to be used by data analysts. Accuracy, which also run a symbolic interpreter, and it's going to be used by the data analyst. And DPella, that actually run the query, and for that you need to set up the privacy budget. That's the data curator. Okay? So, that was the library, 450 lines of code. Okay? And in the remaining of the talk, I'm going to tell you some experiences and reflections that I hope it will be interesting and maybe useful for you, how to take this into a commercial setting. Okay? So we will change the slide so you know that now I'm talking about DPella the company, not the DPella the research. Yeah. So I'm going to present you the team, the technical approach that we embrace, one of the innovations, and some reflection that have changed the way I think in academia as well as in the company. Right, the team quickly is my co-founder, Marco Gavardi, an expert in differential privacy, and myself. We are the founders. We have one business person specialized in business-to-business companies selling to companies. And then my former PhD students who have survived, Agustin and Elizabeth, have survived the education and now join the company. Okay? And then we have some advisory board and some investors. But it's like pretty small. This is kind of I'm pretty academic, so I'm super proud of that. Yeah. Yeah, so the technical approach, we're going to use Haskell. Okay? But we're going to follow 3 principles, which are as follows. We are going to make all the product as embedded as possible. That means let the compiler do most of the work. It will use strong typing disciplines to ensure the correctness of the implementation of the different differential privacy mechanism. And you saw that a little bit when we keep track statically of the stability of the tables. That will be used then to check the noise, and we take that information from the type. Right? So we know it's correct. And then we embrace static analysis. We want DPella to apply as much static analysis as possible. And you saw a little bit of that with budget and accuracy, where I analyze the query without even running it. Right, but this is my well-typed island, right, which is like amazing. But then we face that, the rest of the world is usually untyped. You get HTTP requests, you get data schema specifications. If you think like, oh, a data set, I represent it with a data type in Haskell. But if the data set is specified at runtime, how you prepare your system to give you any sort of guarantees, right? And then we need to produce outputs which are untyped. But that's no problem because it's from typing to untyping. That's okay. The tricky part is this part. Right. So the product has a strong reification phase, and this comes from normalization by evaluation. It's inspired the name by that. If you know normalization by evaluation, it's a way, yeah. This is very sensitive, so I wouldn't say it's a way to specialize program. That's okay. It's a way to specialize programs. And there is one aspect of that maps semantic values into normal forms. And for me, the semantic value is the untyped things, right? And the normal forms is, we don't have normal forms, but we have data type representation. But we just took the name, not the technique, eh? So I want to be clear, yeah. Yeah. So it's a lot of reification phase. All right. Let me show you one technical innovation that we are doing in the company. This is one of the transformations that I show you quickly. DP select. It means like give me a data set and a function, and I will map the function over all the rows in the data set. It turns out that for this to be sound, to this type to make sense, this needs to have sensitivity 1. The Haskell function has to have sensitivity 1. How do you compute the sensitivity on arbitrary Haskell function? Well, people have looked into that. The pioneer of that work was FAST by Reed and Pierce in 2010, where they showed how to build a programming language where you write higher functions and then you can compute the sensitivity of them. Okay? And that spawned a lot of different work, but they require like what I will call heavyweight programming language theory. Linear types, modal types, dependent linear types, and so on. But remember, we want Haskell to do most of the work, right? So we don't want to just bring another language. So we figured out that it's enough to use parametricity, a certain flavor of parametricity, and then you can get the sensitivity calculations that FAST is doing in the same way. And every time that Haskell type check, Haskell will provide a proof that the function that you've written has certain sensitivity. And this is under submission. All right, to wrap up some reflections. that get me thinking after I started the company. One is about legitimacy. We are academics, right? Right. How does the word legitimate what it means? It means like my boss needs to be an academic, otherwise it will not work. Because my boss needs to have the same experience that I have. I need to admire my boss, right? And that happens in business as well. This is how you organize. This is one way to organize companies called the functional way, where you have different compartments based on certain functionality of the company. You can think that this is your computer science department as well. Instead of product X, say research group X. Then you have marketing, finance, and so on and so forth, right? In business, there is one invariant for organization, which is like research and development. The boss is always one of them because of this legitimacy that I was talking about. Marketing, finance, it doesn't matter. But in research, there are sophisticated people, right? And, that made me reflect about myself, right? So I got to the position where I am, and I guess, like many of you, it's like we are technically strong, we can articulate complex ideas in simple terms, this is what we do down here. But then when we go up, we progress in our academic careers, the type of set of skills that you need are completely different. Right? Are completely different, and there is no way that I could hire someone to fill that gap. Because remember, legitimacy needs to be us. Right? It needs to be us. So we need to train, well, at least I train a lot about some very simple management practices, which is not rocket science, but you need to know them, and it makes completely different. How, completely different. It did for me a completely different in the academia as well as in the company. Right? How you motivate people. We got PhD students that are motivating already from the beginning to work with us. In a company, it's not like that, right? So, yeah. Anyway, so that legitimacy, remember, legitimacy is not going to be you who is the boss, but that doesn't mean that because you were famous about writing papers, you're going to be a good boss. That's kind of the reflection. And the last one is about the strategy. You have been in department meetings about, I guess, strategy for the department in the 5-10 years, and everyone is super obsessed about the strategy, right? I'm not saying it's not important. It is important, but there is another factor, which is, which I will show you now. This is from a course I did in business, where it shows how much a strategy impact in the success of a firm. It has an impact, yes, it has an impact. But the thing to watch is this. Most 50% of the things that affect your success come from unknown things that you don't control. And when I read that with my mind, academic mind, I said, this is bollocks. This cannot be. And then I started reflecting about how I became a professor, right? My strategy was I want to go to Chalmers, right? I applied, I got rejected. So I didn't get the chance. Then in 2005, I met who was my advisor, Andrew Sabelfeld, in an event, and he said, I'm looking for a PhD student. And the reason that he was looking for a PhD student was because 2 weeks ago, the one that he hired decided not to come. Then I got the position. Then in 2010, there was an opening for professorship in Chalmers, and I decided not to apply. I was confused by them, because I was doing a lot of security. I consider myself a security guy, not a functional programming guy. I have some identity crisis. Now I understood I'm non-binary, right? So I'm both. So I decided not to apply. And then Kuhn Klassen, a colleague of mine, just when I was going home, I came in the corridor and say, hey, Kuhn, Alejandro, did you apply? No, I'm not a functional programmer. No, you are, blah, blah, blah. He convinced me, I applied. Did I win? No. I was second. The first one, Dimitri Vitivinois, didn't come, then I got it. All right? So now when I look back at this, I say, well, maybe it's not that bollocks, right? And my reflection is like, have your strategy, but then be exposed to luck. Try to talk to as many people, try to do as many things as possible, because you never know where the lucky part will hit you. All right? And with that, I will wrap up and happy to take questions. Thank you very much.
Can I go? Okay, so if I understood correctly, you're piggybacking the sensitivity analysis on Haskell's type system, but the accuracy and privacy budget tracking, that's a separate static analysis.
That's a different static analysis.
So is there a reason to prefer you doing the sensitivity analysis in the type system instead of also doing a separate static analysis, or?
Yeah, so question. I think what we wanted to do, we wanted to piggyback in the compiler, and if the compiler, when the compiler type checks, the compiler provides a proof. We didn't want to write our static analysis where we need to encode the proof there, right? So we say, if we assume that the Haskell type system is correct, then the type system, when type checking, will do the proof, right? That's the reason.
And then going the other way, is there any hope to do what is currently a separate static analysis in the Haskell type system, or are those things too hard to encode?
That's a good question. This was the simplest way that we come up, that, yeah, why we did like a symbolic interpreter rather than at the type level. Simplicity, I would say. Because I mean, we published this in Security and Privacy, which is a security conference, and then it's good when you publish there that you don't put super crazy types. Yeah. So, but it's I don't know. Maybe it can be done at the type level. Everything. I don't know.
Thank you.
Thanks for the excellent talk. So I was wondering about the parallel composition that you mentioned in the background, right?
Yeah.
Are you actually using it? So you had the example with the European and Latin American, right, nationality, but you mentioned in your database you can have both nationalities. What if you could have only one here? Could you apply the parallel composition with your tool?
Right. So, yeah, that's a good question. Let me show you how we enforce that. Yeah. Here. So this is what we do parallel composition. It's a partition. So you need to specify up front a mapping for every key that you're going to partition the data, and for every key you give me a function from that partition into a query, and a function that maps. This function needs to be correct. So it means like the thing here can never map one record into two keys, right? And you can see here that that's not the case because. Yeah, for every record you apply, it's a function, so then it will map it to only one key.
Okay, so I have to use this function if I want to.
Yeah, when you use partition, that's what encodes the parallel composition principle. Yeah.
I have also just another question. I didn't really understand how you track the budget. Like you had this thing where you gave too much epsilon, and it told you, the language told you don't have enough budget. How does it work?
So what we do, we traverse the query, and we look for all the measurements. And when you find the measurements, in the simple way that this is a very simple way to compute the budget. There are more complex ones, but we traverse the query, and then we find all the measurements, and we just take the parameter there.
But does it work if you have different queries, or if I use your evaluate, or does it have to be enforced at the end of the day by the data curator?
Yeah, totally. So
okay,
the data curator will call budget and check, is the budget that this query requires enough? Sorry. Yeah, they have enough budget. I have enough budget to satisfy this query. If that's the case, then it will go through.
Okay, thank you.
Are there any other ways of preserving privacy than just inserting noise?
Yes.
What notion of noise actually in general you mean? There are various noises you can...
Usually most of the techniques you can, well, there are many, but I mean, in a system like this, if you can sample from Laplace and you can sample from Gaussian, that's about it. Those are the two distributions that most of the people use in the differential privacy community, right? For this type of systems. Yeah. So these two are this enough. Is that, sorry, that's what...
In other ways other than inserting noise.
Yeah. So there are, I didn't talk about it, but there are some what is called data anonymization techniques, which is you take a data set, right, and anonymize it, which means like you make sure, for example, that every time that you do a query with a certain profile, you always return at least K people, or, and this is called K anonymity. But all of these techniques are not strong about what happens in the future. When you anonymize a data set, it could happen in the future, another data gets available, combine it with this, then you de-anonymize the people. So there are techniques, but for me, this is the gold standard, right? There are other ones that even industry uses, but they are not strong against this future protecting privacy.
I have 3 questions. You can answer any one of them. So first one, following up on previous one, is what if we about the about the precision of the accuracy, for example?
Yeah.
So you very often need amortization techniques in practice. Doesn't seem to be the case here. For example, amortization techniques. So for example, if you had the query there, it says like, you got the Europeans and whatever, Latin Americans, and before actually going to the output, you actually eliminate the duplicates, okay? So, do you get, what's the accuracy of this one? Because this is basically identity function now, so you should have 1, right? But what do you get here from the analysis?
So
that's the first question.
Yeah. Well, in that system we don't do that. In the company we do that. So in the company we do more. We put more static information on the transformations, so then to deal with these kind of cases.
So in that case, you would get actually that it's just basically identity. So it has accuracy, or it has a budget of 1 as opposed to 2.
That's right. The sensitivity of 1. Yeah. If you remove duplicates when you do the union, right? Yeah.
That would be really interesting to see, but I guess you have a company for that reason.
Yes.
The second part is looking at these things. Actually, database systems have 2 things that are really, really cool, I think, and are very important, namely atomicity and transaction. So concurrency control, you wouldn't leave that to an application program. And the other one is join queries. So there's no joins in there. So
no joins are tricky, because when you do join, the sensitivity. So when you do a join, the sensitivity can go to a roof, and people have looked into many different ways to address this problem, and I'm not convinced about any of them. So we don't have it. So what we say, on the company side, we say to customers, is like, give us the whole data set, and that's usually the case so far. Right.
Last question. Yeah. What was your pitch? You have 30 seconds up the elevator. You had actually 2 VCs there, and they will actually not look at this. They will say like, what's the business value? What's the business pitch?
Right. So what we say is like we do analytics on personal data without compromising privacy, and this will be needed. Yeah.
Okay. Where's the market?
Right. I was going to that. Yeah. And that's what we needed for most of the B2B businesses that are collecting personal data aggressively today. And the market is projected to be around 20 billion or something. I don't remember the numbers right now, but I can give you that. Yeah. So it's a analytics market, GDPR regulations market, data masking market. This is the target addressable market, service addressable market, service obtainable market. Yeah. So you know about that. Yeah. Thank you. Yeah.
Yeah. Thanks for the talk. So one question that I had was, you compute the sensitivity in sort of a compositional way here, and you do this by letting the user, the programmer, specify how they want to spend their error budget, right?
Right. The privacy budget. Yeah.
The privacy budget. Now, you could consider an optimization problem, which is that you want to get the best possible accuracy for your total budget.
Totally.
So have you considered this, maybe by computing some kind of a program transformation that gets you a function of the local budgets, giving you the total accuracy?
Usually, to squeeze from the same budget, to squeeze a lot of accuracy, it requires to go into algorithm design, right? So which is not something that I haven't seen how automatize that. Here is pretty simple, but one of the things that when I show you 3 different ways here, I'm rewriting the algorithm in a different way to squeeze out more accuracy with the same budget. But you need to go into writing code or designing algorithms, right? So I don't see as an optimization, you come with a problem and, I haven't seen yet patterns where it's clear to say, oh, do this pattern, then you will squeeze out more accuracy from the same budget.
All right, yeah, I wouldn't expect this to happen push button automatically, but you could at least try to compute some kind of a function of the local privacy budgets from your original source code, and then use some different analysis on that, if that makes sense.
Yeah, no, it makes sense. I don't see, no, it totally makes sense what you say. But I think this is part of the future research, I guess. Yeah.
Right. Last question. Any more? Right. If there's no more question, let's thank the speaker again.
Thank you.